our guest speaker for this evening. Professor Mohanan is an eminent and renowned name in theoretical linguistics, and his later and other interests include education, pedagogy, scientific and critical inquiry. And it is a great pleasure to have Professor Mohanan here with us this evening, as well as for the next couple of days in which he is engaging with us in a few more events. And I thank Dr. Rajakrishnan for, my colleague Dr. Rajakrishnan, who is the linguist in the department, for his efforts in coordinating this visit. I thank Professor Mohanan for his time, and I will now hand over to Dr. Rajakrishnan, who will formally introduce Professor Mohanan, and then we look forward to Professor Mohanan's talk and interaction after the talk. Thank you.
So thanks for showing up at 5 p.m. Amidst your busy schedule. Professor Mohanan completed his PhD from MIT. His work was on the sound patterns in phonology, and subsequently he taught at Stanford University and then National University, Singapore. In 2011, he was invited to IISER Pune, and he himself has confessed as to taking voluntary retirement from linguistics back in the year 2000. Subsequently, his interests have been much more broader in scope, in general epistemology, philosophy, and in general inquiry as well as research. So inquiry encompassing a broad range of domains, not confined to particular disciplines, confined to the silos of particular disciplines. We didn't expect such a big turnout, so thanks for all of you who have joined us today evening. I would like to invite Professor Mohanan for his talk.
Okay. Thank you for the kind introduction. Thank you for inviting me. This talk actually is not my talk. This talk is what my wife and colleague, Tara Mohanan, should have done. She wasn't feeling physically well, so she has asked me to give this talk. And it's very hard to give somebody else's talk. So that's why we had this handout to make sure that I don't deviate from her talk, which is not going to be the case, so I will deviate a little bit. But on the other hand, since you have the handout, you will have a rough idea of what that talk is going to be. I want to begin by introducing myself to you in my way, and you will see that this introduction has a certain reason, but only later. So let me begin by making the following statements about myself. And I'm going to make 5 statements. I was born on 13th February 1947. Second statement is I am a mathematician, scientist, philosopher, educator, painter. This is self-introduction. Third, this is where it is becoming interesting. Had I been born in 1987, I won't be here talking to you. Why? Why? Because I'll possibly be a painter, but not the rest of it. And why is that? Because, let me tell you why. But before I do that, let me also say that this is the part that I have been pursuing most of my life to help students. After I resigned from linguistics, that's the part that I have been pursuing to help students become mathematician, scientist, philosopher, educator, not this, because that's a private enterprise. So in other words, what I'm trying to do is to clone myself. That's my fifth statement. And I think all educators try to do that. What they are good at, they teach the students to be that. So I'm not going to teach you how to invest in stock market because I'm hopeless at that. I'm not going to teach you in how to find places and so on, drive. I'm directionally challenged. So why bother to teach things that I'm not good at? Let me try to explain why I think I wouldn't be here had I been born in after 1987. This is because the nature of the education system has changed remarkably. When I was a high school student, when I was an undergraduate student, I did not attend classes. I went to the library, I had conversations outside, and I survived because my friends were good at proxy attendance. And I also have done that for my classmates. Like I could do proxy attendance for at least 10 people in one class. And I was admired for my proxy skills. I was extremely bad at answering exam questions. I barely scraped through. I passed because my friends insisted I should learn something, at least to pass. And I survived. In those days, that was possible, to do badly in your exams and still go through an undergraduate degree. But I don't think that is possible now. So if I were born at this time, by the time I got to the undergraduate stage, I would be doing multiple choice questions, and I can't do that. If I took, for example, the PhD entrance examination to my own discipline, linguistics, I would flunk. I won't get 20%. So there is no chance. For people like me, higher education is impossible now. And I wonder how you guys are sitting here. Maybe you have learned to cope with this system. You have some skills that I don't have. So I really admire you. Okay, what does that mean by my saying that I'm very bad at examination questions? But there are certain other things that I'm good at, because I mentioned mathematics, scientists, etc., science, etc. And I want to make a distinction between exam questions and research questions. And the gist of my talk today is about this. I'm saying I'm not good at this, I'm good at this. What's the difference? So let me ask you this question. Suppose you have a multiple choice question. What is a right angle? Or what is a right angled triangle? So I give you these options. A right angled triangle is a triangle with one of the angles 45 degrees, one of the angles with 90 degrees, one of the angles 180 degrees, one of the angles 220 degrees, none of those. I'm pretty sure you can take about 2 seconds and say 90 degrees, right? That's an exam question. Is it an interesting question? No. I would also like to convince you that even though all of you are good at answering that question, you don't really understand that question, except some of the mathematicians here. I will do that a little later. So you can answer these exam questions without really understanding the answer that you're giving. I know that you don't believe me at this point, but I'll try to convince you that that's the case. Now, let me ask you a different kind of question. This is an exam question. Let me give you 3 examples of a similar kind, which are not exam questions. Do straight-angled triangles exist? I'm pretty sure you haven't seen a question like that in an examination, and you may not be able to answer this as a multiple choice question because it'll take you at least 10, 15, 20, 30 minutes to grapple with this question. Multiple choice questions are supposed to be answered in 2 minutes. I don't think we can really do that. And I'll show you why it takes time by going through that question. Do white crows exist? And does God exist? Now notice that all of these are of the question, of the form, does X exist? And you can replace the X with other things. Does consciousness exist? Does free will exist? Do black holes exist? And so on and so on. This is the type of question, this is the type of research question, and that type doesn't belong to any particular discipline. So this question is about mathematics, this question is about science, this question is about religious philosophy. It doesn't matter. And you will see that addressing such questions, it's the same throughout. It doesn't matter whether it is mathematics or physics or biology, it doesn't matter. My interest is in questions of that kind, not specific questions in particular disciplines, but in question types. How do you answer this kind of question? And if your answer is yes or no, how do you prove it? It's existence proof. Existence proof has some differences between, let us say, mathematics and sciences and so on, but they have roughly the same broad kind of structure. Let me now try and see if this question makes sense to you. Okay. Notice that to answer this question, you have to know what a straight angle is. And I'm assuming that all of you know that because this is part of your primary school learning. What is a straight angle? Yeah? 180 degrees. Okay. So if you have A, B, and there is a C here, this is a straight angle, right? Okay. So the question is, do straight angle triangles exist? You have to define a straight angle, which you have done, and you have to define a straight angle triangle, and you can say a straight angle triangle is one in which one of the angles is 180 degrees. Okay. Do such triangles exist? How many people say no? Raise your hands. Okay. How many people say yes? Raise your hands. Okay. Now here is the challenge for you. Both answers are correct. Okay. So this cannot be an exam question. Because if I ask you the question, do they exist, and some people say yes, and others say no, and I have to give full marks for both, this doesn't work as an exam question. Okay? To convert that into an exam question, I have to do something else. I have to add to this question the following instruction. Whether your answer is yes or no, it doesn't matter, but prove it. The answer is graded on the basis of the proof, not yes or no, but the kind of proof that you give. So I noticed that the people who said yes are the people, that's a smaller number. So I had two choices. One is for me to go through the rough sketch of the proof, and the other is to, what I usually do is not lecture on the proof, but get the participants come up with the proof. That's what I normally do. I was almost going to do that, but it will take time. I will not be able to come to the language data in the last page of the handout. I would very quickly go through some of these issues to give you a very broad sense of what it is like to do research, to address research questions by taking a few examples of this kind. Now, suppose you say yes, the minority people here. How will you prove that? Well, first of all, you have to define not only straight angle triangle, but a triangle. So you begin with the definition of triangle. And let us say a triangle, angle. There are many ways of defining triangles, but here is one way which is perfectly okay. Triangle is three vertices connected through straight lines, and only straight lines and so on. Roughly, that's the idea, the three vertices, and you connect them with triangles, with straight lines. Now the question is this. So far, okay? Let's take a triangle ABC and bring this point down. Okay, so it'll look like this. Bring this down further until C is here. So it'll look like this. Now the question is that a triangle? According to the definition, it is a triangle because there are three vertices. Here is one vertex, here is another vertex, and here is another vertex, and this is connected through straight line AB, and straight line AC, and straight line CB. Is that proof okay? Even though it visually doesn't look like a triangle, according to the definition, it is a triangle, as she said, right? So you have to free yourself from the visual prejudice. Okay? And this is what math is about. Geometry may begin with vision, but at some point you have to get out of that prejudice. You have to liberate yourself from what you can see, because a line is not something that you can see. Why? Because notice that if I say that's a line, and the definition of a line, or at least the concept of line that Euclid presents is lines do not have breadth. But this thing has breadth, so what I have drawn here on the green board is not a line, it's a rectangle. There is a little bit of breadth. I cannot draw a line, because no matter how thin, line has some degree of breadth. If I take a pencil without but as a point which has no dimension, then you will not be able to see it. You can only see it in your mind. So you see it in your mind, but not with your physical eyes. That's what geometry is about. It's an abstract entity, not a concrete entity. What I have drawn there is a representation of that abstract entity that I call line. And the triangle is an abstract entity. You have to, it follows from the definition that this is a triangle. It fits the definition, therefore it's a triangle. But then what are the logical consequences? Notice that you already said, since that is a straight line, this will be 180 degrees. We have the theorem that says that the sum of angles in a triangle is 180 degrees. If that is the case, the other two angles must be 0. That's a logical consequence. There is another consequence which says that in a triangle, it can be stated in two ways, that the sum of these two sides must be greater than this side, is the triangle sum theorem. The way I said it, the sum of AC and CB must be greater, that is violated here, it is not greater. Right? So that theorem stated that way is false in a straight angle triangle. Is that okay for everybody? Okay. How should I state it? There is still some truth, some part of the truth in that. What I can say is this, that AB should not be greater than the sum of these two sides. That is maintained here. So the theorem, the logical consequence of saying that this is a triangle is in the theorem. So is the theorem the sum of the sides must be greater than this? Is that true? That depends upon how you define triangle. Now some of you said that this is not a triangle. And I said that answer is perfectly okay, but you have to prove it. So what that means is that you have to define triangles in such a way that this is not a triangle. Okay? So in other words, you cannot allow any angle to be 180 degrees in a triangle. There has to be some magnitude more than 0 for the other two angles. How will you define it that way? Anybody who has ideas on that? Okay. It's always a good idea. Yeah. Well, you want that to be a theorem, right? So do you want to say that as a definition?
Only greater than.
Yeah, but you're saying in any triangle, no angle should be 0, right? Well, if you define it that way, that's okay. Then it automatically disallows this kind of stuff. But can you define a triangle differently without making this a theorem instead of, yeah.
Counter that argument, we can say that if we say that there is a triangle whose angle is 180 degrees, then we can state that any straight line, if we draw and we mark 4 or 5 points, we can represent that as a polygon, right? By stating that there
yes.
are kind of vertices.
Absolutely. Absolutely. Now okay. I wasn't planning to introduce this, but the notion of straight angle creates a huge problem unless it is carefully controlled. Reason. In any straight line, AB, you have infinitely many points, right? So take any point on a straight line, you get 180 degrees. What is the sum of angles on a straight line? Infinitely many 180 degrees. What is the sum of angles in a triangle? Infinitely many. So the theorem that the sum of angles of a triangle is 180 is obviously false if you allow that. Of course, you need to disallow that. Otherwise, the whole of geometry is in trouble. I'm not going to tell you how that can be disallowed because I know that this will create some discomfort. And at least some of you will start thinking about it at night when you're falling asleep or when you're eating your breakfast tomorrow morning or you're talking to your girlfriend or boyfriend and the other person would say, what kind of creep are you? You're not listening to me. Right? That's the disadvantage of starting to think. Which, as I said, my job is to make clones like me, and I always face that kind of danger. So I'm not going to solve that problem for you. It is for you to solve. I'm not going to solve the other problem either. How can you prove that this is not a triangle? You can do that if you define triangles, right? Again, I leave that to you. Yeah.
So we can say that a triangle is it is a closed figure with 3 sides, and we can't say that a line is closed figure.
It is still a closed figure depending upon how you define closed figure. I start from here, CA, BB, and this. Why isn't that a closed figure? Yeah. Pardon me?
Vertices are not collinear.
Okay, if you say in the definition 3 non-collinear vertices, these are collinear, absolutely. So this is not a triangle. If you add that word, then your answer is no. It is not a triangle. Then of course, what is the answer to the question? Can straight triangles exist? Your answer is no. So notice that both these answers are correct, but the truth of the answer depends upon the assumptions that you make. This is a very important aspect of mathematics, to understand the relation between the assumptions and the logical consequences. Truth is a function of the assumptions. Truth is a true proposition is one that is rationally justified or rationally proved. Both these propositions can be rationally justified. Okay, now this is the flavor of what it is like to think like a mathematician. Notice that there is no calculation involved in any of the things that I said. It's pure abstract thinking, not calculation. Calculation is important in mathematics, but more important is imagination, insight, thinking abilities, reasoning, precision, clarity, etc. That's what math is good for. I am not good at calculation, because if I add, let's say 5 numbers, I get 6 different answers. I have never been good at that. I always lost marks in adding. The things that I cannot do in math is addition, subtraction, division, multiplication. I can do other things. Now you said that right angle is 90 degrees. How do you know whether something is a right angle or not? Well, you can say if you have a line like this and a line like this, you can put a protractor there, and if it coincides with this, that is 90 degrees. But notice that you cannot see a line, right? If you cannot see a line, how are you going to measure the angle? Those two things that I have put there are invisible entities. How will you measure right angle 90 degrees? So you cannot give me an answer 90 degrees because this is part of science, not math. How would a mathematician define right angle? How would a mathematician define perpendicular? If lines are invisible things and you cannot use a protractor. 90 degrees makes no sense. This is what you learned in primary school, but that was, you learned geometry as science, not geometry as mathematics. Okay, so every educator is a torturer. Why? Because it is mental torture for you to have this question in your mind and not get an answer. Why do you believe in torturing students? Because something good comes out of it. Because you will be thinking about it, at least some of you, as I said, when you're riding a bicycle or talking to your girlfriend or boyfriend, or eating a dinner, or having a shower. That is when real learning takes place, not when you're sitting in a classroom listening to somebody giving a lecture. The real learning takes place when you're by yourself or talking to your friends outside the classroom. The learning that takes place in the classroom is about 10% of valuable learning. A teacher is simply a trigger for learning. The actual learning is done by you, not by the teacher. So what do teachers do? They ask these questions and they will throw things at you, and you figure out answers on your own. And then of course you can discuss the answers with your teacher later, but only after you have put in the effort, you have struggled with the question. Now let me go back. Yeah.
You told to define the perpendicular lines without using the protractor. So we can define it by drawing a circle and then cutting a tangent to it and connecting the center to the point of intersection. Then we can define
You can. So one path that you're suggesting is you take a circle and you take a tangent, and the angle between these two is right angle, right? But now you'll have difficulty in defining tangents and all kinds of things. Doesn't matter. This will do for now. There are much better ways. This is okay for now. Okay, this is a good idea. It works. But let me give you a clue of thinking about angles. An angle is simply a measure of rotation. So if I take this, imagine that this piece of chalk is a line, and I'm rotating it all the way, and I come back to the same point. Okay, that's what you call 360 degrees, right? Napoleon decided that it should be 100 degrees, not 360. That's an arbitrary number, because if it is 100, it's like the decimal system. Had Napoleon won the war, you will be defining right angle as what? 25 degrees. It just happens that Napoleon didn't win, and therefore 90 degrees is now conventionally, right angle is conventionally 90 degrees. But the idea of right angle is the same whether it is 25 degrees or 90 degrees. What is that idea? Is what you need to answer. Yeah.
Shortest, if you take a line and then take any point, is the shortest distance between the point and the line.
You're saying you take any line and any point, the shortest, but if it is a straight line?
Not on the line, outside that.
Okay, so any point outside the line? This is what? Right angle?
No,
it's a curve.
Shortest one.
You know, if it is a point outside the line, like that,
Yeah.
are you saying that AC, this is a right angle?
No.
Huh.
Now I just play with I start drawing lines to that line.
Okay.
That point.
Yeah.
And until I get the shortest distance.
Uh-huh. How does that help me to define right angle? Yeah.
1/4 of the rotation.
1/4 of a rotation. That both Napoleon and the other guy would agree that's the right angle. You don't have to measure things. So the notion of angle is built on rotation. Yeah.
If we take a circle and take the diameter of the circle, right, and we draw any two lines from the two endpoints.
Okay. Right. Yeah. So what he's saying is that take a circle, draw a diameter, take any point and connect. That will be a right angle. Notice that you want to keep that as a theorem, right? Do you want to use a theorem as a definition? It's your choice. Right? It is definitely possible. This is one of the things that you learn in math, that you can exchange theorems and definitions, you can exchange axioms and theorems.
I actually don't remember the person who came up with this, but I think he defined a circle by stating that this is 90 degrees.
I see, okay. Yeah, but that's perfectly okay. But if you try to develop that theory, in which that is how you define circles and so on, you will find that it will be very hard to go forward. I'm not denying that in principle. Try it out. Okay? The only way to check whether it works or not is by really trying it out yourself. So these are the kinds of things that you do in research. Let me go back to the original idea. These are research questions. And notice that one question, do right angles exist? Do straight angle triangles exist? Notice that it led to so much discussion, so much thinking, collective thinking. It is not something that you can answer in a multiple choice question. So when I said I'm very bad in answering exam questions, what I meant was these exam questions that have to be answered in less than 2 minutes. I cannot deal with any such question, because I look at that question paper and look at that question and say, that's an interesting question, let me think. I flunk. I don't have the luxury of spending more than 2 minutes per question. So people like me cannot do well in multiple choice questions. We are handicapped. Okay, so the last 20 years of my life has been waging war against MCQs that will not allow more than 2 minutes per question, because it handicaps people like us. We may be somewhat strange species, but why should we be handicapped by the examination system? We should also have a chance to pursue higher education. Okay, these are the people who are discriminated against. Okay, this wasn't meant as an introduction to mathematical thinking. This was meant as an introduction to addressing research questions and the difference between addressing research questions and addressing exam questions. Whatever I have illustrated will also apply to other things, to the other questions that I raised. For example, do white crows exist? You have to define crow. Because if you see a white bird and say that's a white crow, I might say, no, that's not a crow. So unless you define crow, you cannot investigate the question whether white crows exist or not. So definition is not simply a property of mathematics. It applies in science, all sciences. So if you say something like two things belong to the same species, like foxes and dogs belong to two different species, or Alsatians and poodles belong to the same species, you have to have a definition of species without which this doesn't make sense. Okay, and that's not easy. Why? Because the textbook definition of species that all of you have learned is that two organisms belong to the same species if and only if they can mate to produce a fertile offspring. Sound familiar? Right? Now, pay attention to that definition. According to that definition, do Raja and I belong to the same species? Raja is this person sitting here. We cannot mate to produce a fertile offspring. Right? So any two male members of whatever things belong to distinct species. That's the weirdest definition of species that I have ever seen. Its logical consequences are clearly false. I mean, false in the sense we don't accept those consequences. Do bacteria who reproduce sexually, asexually, do they belong to the same species, two members of bacteria? No. Any two bacterial organisms belong to two distinct species. So we have to find some other definition of species. You look troubled. I can see that you're troubled because this is what you learned in your school. But it's about time to start thinking about what you have learned and asking the question, did I learn what I should believe? That's a different question. I'm not talking about exam questions. Exam questions, you tell the examiner what they want to hear. But that's very different from knowing something. You don't need to understand what you're saying in an examination. You don't need to believe it. But outside of the examination, when you start thinking for yourself, then the world changes. All right. I'm trying to decide what example. I have given a large number of examples in the handout. Obviously, I don't have time to go through all of them. So I will pick, since I picked mathematics first by way of introduction. Oh, but let me, before I do that, let me tell you something about an important concept in academia, the concept of theory, which is where all this hinges on. What is a theory? Okay, a theory is simply a combination of set of premises, conclusions, and the reasoning that connects these two. So there are some propositions are premises, other propositions are conclusions, and there is a reasoning from premises to conclusions. And in mathematics, you refer to this as theorems. In science, you call them predictions. A logician will tell you that these are logical consequences. They mean the same thing. And premises in mathematics are definitions. We had some examples to show how the way you formulate a definition can affect the truth of a theorem. Then there are things that you call axioms, postulates. The distinction between axioms and postulates is not important for us. Euclid made a distinction, but for us it doesn't, at this point doesn't matter. All that matters is that definitions are definitions of concept. Axioms are statements that you take for granted as a starting point, or postulates a starting point, in order to proceed further. And you can include these as assumptions. If you make certain assumptions, certain logical consequences would follow. That's what a theory is, but there is an important condition on this structure. One of this, of course, you have to prove that the conclusions follow as logical consequences. And the other condition is no logical contradictions. So these two things, these two concepts, logical contradiction and logical consequence, are the pillars of rationality. If you abandon these two things, rational inquiry is impossible. And a theory, whether it is mathematical theory, scientific theory, philosophical theory, all of them have this structure, or ought to have that structure. The difference between math and science is the following, that in math, once you do this stuff, your job is over. You don't have to prove that the assumptions that you started with are legitimate assumptions. In science you do, and what you do is you show that these logical consequences that we call predictions match the observed generalizations. That's just an additional component in science. But what is common to all of them is the other structure. What that means, yeah. Reasoning can also be? A theory itself. What are the... Yeah. So these are theories of logic. Yeah. So mathematician uses logical theories to prove things. But then somebody might ask, why should I use those ideas? Then you have to go to the next step, which is logic. Logic as a foundation for mathematics. Just as mathematics is a foundation for physics, physics is a foundation for engineering, logic is a foundation for mathematics. Yeah. So what that means essentially is that if you want to be a good scientist, you have to learn this, but you also have to learn logic. And not just one logic, but different kinds of logic. I'm not going to go into those details. The reason why I'm saying this is simply because some of you might look up types of logics, two-valued logic, three-valued logic, inductive logic, diffeasible logic, and so on. There are various kinds of things. And it will be a good idea for you to learn those things, which obviously we can't do here. Now, why is this structure important? The structure is important because we need to make a distinction between knowledge as information and knowledge as understanding. So when I said that I was born on 13th of February 1947, that is just a fragmental piece of information. And when was I born is not a research question, that's a piece of information. But if I ask you, when was Panini, the Indian grammarian, born? That can be a research question. But the outcome is still a fragment of information. But when I said, likewise when I said, what is what is a right angle triangle? That's a piece of information. But when I said, do straight angle triangles exist, notice how it expanded into various things. It had a certain structure and then led to certain understanding. And it's important to distinguish between knowledge as pieces of information that you can get from an information counter and knowledge as understanding, which is connecting these pieces into a coherent whole. So if I take a bottle, which is a unified object, throw it on the floor, it breaks into several fragments. Those fragments are like pieces of information. A telephone directory is simply a bunch of information pieces. You can't connect them into a coherent whole. It's like broken fragments of bottle. But if you put back those fragments back into a bottle, then that's like a theory. A theory is that which gives you understanding by structuring information into a coherent whole. So people talk about things like coherence, people talk about beauty. All these are consequences, understanding, all these are consequences of structure of information. And that's what a theory does. And what I've illustrated here is how reasoning plays an important part in structuring information into a coherent whole. And you should also have another component is truth. Truth or belief or credibility, whatever. Understanding is not sufficient to call knowledge, for example. I understand the geocentric theory, the theory that says the sun revolves around the earth. But it is not part of my knowledge. Why? Because I don't judge that theory to be true. But I accept the heliocentric theory because I judge that to be true. Now that is part of my knowledge. Notice that reasoning is an important part of understanding as well as judging something to be true. If your judgment that something is true does not depend upon reasoning proof, then you don't have knowledge, right? Now let me ask you a question. Does the sun revolve around the earth or the earth revolve around the sun? Which one? I mean, this is a trick question. I know what you're going to say. Of course, the second one, right? So can I say that you believe that the earth revolves around the sun? You do, obviously. Why? Why do you believe that the earth revolves around the sun? In the case of my date of birth, some of you probably believe that I was born on the 13th of February 1947, but I may have been telling you a lie. Alternately, maybe my parents misled me. I was actually born on, January 13th. But maybe it was a bad day, so my mother thought I'm going to tell my son that he was born on the 13th of February. I never asked her. So maybe it is not true. But what I do is, well, I have no reason to disbelieve her. So it's okay, it's not a big deal. It doesn't, for me, it doesn't really matter whether I was born in February or March or January. But that is not the case with the earth revolving around the sun. Why do you believe that? What are your reasons? Can you prove, as in the case of mathematics, can you prove that this is the best belief? This is actually another part of my torturing, incidentally. I am asking you this question because I'm pretty convinced that you will not be able to answer the question. Yeah.
Sir, if we talk in terms of mathematics, then I cannot really prove, but if we talk in terms of science, you can say science can be defined in terms of, first is theory, understanding the theory, then experimentation, then verification.
Yeah.
When we are having a particular theory, like we have the theory of the earth revolving around the sun, we are having experiments conducted to prove that theory, that the earth is revolving around the sun.
Yeah.
And then we are having the verification aspect of it.
Yeah, okay. Verification is only for the observation generalization, not for the theory. Theories cannot be verified. Okay? There's a difference. So let me sketch the structure of the scientific theory. As I said, you have these axioms and definitions and certain logical consequences follow, and these are called predictions. And the predictions match the observational generalizations. And when the predictions match the observation generalization, you say the theory explains the observation generalization, right? That's what the word explain means. So when I ask you why do you believe that in science, your answer should be those axioms and definitions help me to explain certain observation generalizations in a way that competing theories cannot. So the geocentric theory can explain certain things, but the heliocentric theory can explain many more. And this is a better theory. It's called explanation-based argument. It's not like in mathematical proofs, but that is a different kind of proof. The reasoning is slightly different. So can you identify the observational generalizations that the heliocentric theory can explain, but the geocentric theory cannot explain? That's my question. If you don't have an answer, then you are believing the heliocentric theory in blind faith because somebody told you so. That is a dogma for you. It is not a scientific belief. Yeah.
You can look at the position of the stars to believe that the Earth revolves around it.
Position of the stars. I am not sure what you mean by that, but if what you mean is, if you look at the night sky and look at the positions of stars, you find that the positions of all stars except the pole star keep changing. Okay? You can explain that either by saying the Earth is rotating, or you can explain that by saying the whole globe is rotating around the Earth. Right? Both are good explanations at this point. Okay? Now give me something that the heliocentric theory can explain, geocentric theory cannot. Yeah?
In some regions of the Earth, there is a day for months and night for months. And also we have seasons which can be explained through heliocentric theory. But
you're saying geocentric theory can't?
Because in different places, how can, we know that Earth is round.
Okay. For you, I would say we have reasons to believe that the Earth is round. It's a dangerous word. And I will grant you those reasons. Okay, fine. Yeah, let us accept the idea the Earth is round. Fine. Now, but how do I know whether the sun revolves around the Earth or not? Why should I believe that? So you mentioned seasons. Implicitly you're saying there are certain observation generalizations about seasons that the heliocentric theory can explain, but the geocentric theory cannot. So first of all, what is the explanation? You don't know. If you don't know what the explanation is, you're believing the theory as whatever it says as dogma. It is not science. Okay? Yeah.
So we can position the comets like Halley's comets which passes about the Earth. It revolves around comes the back of the sun and then approaches. It never approaches like around the Earth.
I'm sorry? The comets.
Yeah, sir, I am saying that if a Halley's comet passes near the Earth, then it doesn't move like covering the Earth.
Yeah, but how does that explain anything about the sun revolving around the Earth?
It can be only explained by the heliocentric model, not the geo.
Not really. I don't understand why that should. What is the steps of reasoning? You are making an assertion that the behavior of comets can be explained only if you have the heliocentric theory. That's not necessarily correct because Ptolemy could predict large number of things. So many of the things that we think Ptolemy couldn't predict, he was able to correctly predict. So let's go through this stuff. Yeah.
Sir, at least if we understand the gravitational theory, then it's really that both Earth and the Sun rotate around each other, and in that way everything rotates around each other. So
okay, that's a little too far ahead for this. Let me stick to just two theories. Not that they revolve around each other. that becomes extremely hard. So let's just say two possibilities. One is the Earth rotates, the other is the Sun revolves around the Earth. Let's stick to those two relatively clean things. Yeah. Satellite images can't, because in order to check whether the Earth is revolving around the Sun or the other way around, we have to leave the solar system, go outside of the solar system, observe from a different star. No satellite has done that. So you're still within the solar system, you can't tell. So observation is not sufficient. What you have to appeal to is the ability of the theory to explain things, not direct observation. So this theory cannot be verified. It cannot be justified through explanation.
According to the geocentric model, the other planets were supposed to revolve around the Earth as well, along with the Sun, right? But when we observed it from the Earth, they did not for the expected orbit around Earth.
What?
According to the geocentric theory, the other planets were supposed to revolve around the Earth too, along with the Sun.
Yeah.
But when we observed from the Earth, they did not for the expected orbit around the Earth.
I'm not quite sure what you mean. Perhaps what you mean to say is that how do we conclude whether the planets revolve around the Earth or whether the planets revolve around the Sun? That's your question, right? You cannot observe it, you can only explain, and through explanation you can show that one explanation is better than the other. Now, that part is a little hard, because the crucial part of the explanation for both the heliocentric theory and the geocentric theory is what is called retrograde motion of planets. So so that you can look it up and find out how to explain that stuff. Retrograde motion of planets is like this. If you're from the Earth, you observe the position of planets against the positions of stars. Stars are relatively fixed with respect to each other. And if you observe a planet, you find that the position shifts as you move. So you seem to be moving in this direction. But then you find after several days that it shifts this way. And then it begins to go again. So it's almost like it goes this way, comes back, and then goes back again. So this movement is the retrograde motion. This is the observed movement of the planets. Now the question you should be asking is, how will the geocentric theory explain it? How will the heliocentric theory explain it? Interestingly, Ptolemy had an excellent explanation. So it is not explanation less. So you need to find out what that explanation is. It required crucially what has been called epicycles. I'm not going to tell you what epicycles are. You can find out from the internet. My reason for bringing this up is simply to demonstrate there are things that you believe, which you have been taught in classrooms, but you never bother to ask why we should believe those things. And to the extent that you have never asked why I should believe those things, your beliefs are exactly like thunder and lightning are caused by Zeus. Somebody told you and you believe it, right? You have many such beliefs. Somebody told you so. But that is not a rational belief. These are dogmas. Okay.
Sir, if the sun revolved around the Earth, then there would be more solar eclipses than they happen right now, because the speed of the moon and the sun, the speed of the revolution would be different, and they would cut more times.
Yeah, you have to do that through very careful calculations. Yeah. So
it can be calculated.
If it can be, yes, I'm willing to accept it. But before I accept that position, you have to take me through arguments without involving detailed calculations. So, for example, whether the orbit of the Earth is a cycle or ellipse requires tremendous amount of calculation that Kepler did. So, for our purposes, if you are not going to look at calculations, whether it is elliptical or cycle, it doesn't matter. We can create the arguments. Likewise, whether the angle of rotation, the axis of rotation is 23.5 or not, this is what you learned in primary school. whether it is 23.5 or 25.6 is a matter of careful calculation. But whether there is a tilt, whether it is perpendicular or not perpendicular, that you can argue without calculation. So my enterprise at this point is to take you through the arguments that do not require calculation at the first cut. And then of course you can proceed the arguments based on calculation. But the first part is arguments that do not require technical calculations. Those are the basics. And those are the things that educated non-specialists should understand. The details of the calculation meant for specialists. Astronomers, for example, would need to know how to make those calculations. But why should a historian understand those calculations? No, not important. Why should a dancer, why should a biologist understand those details? But there are certain things that we expect all educated people to understand. Those are the sort of broad aspects of knowledge. And they don't require calculation. Okay, I should point at some, I should stop at some point, and this may be a good time to stop. And we can continue this discussion if you want to ask questions. I'm available till whatever time. No, I'm available till about 9:30, then I fall asleep. So, I guess formally this talk is ended. So we can